Dr. Sasha Jenkins. I'm the lead at the University of Western Australia on the Smart Farming Pilot to Paddock grant. This group is a diverse team. We have soil scientists, we have plant scientists, chemists and engineers. The first part of this project was to take nutritionally unbalanced, bulky product such as manure and basically modify it through composting and granulating and adding in missing minerals and coating it to make it into slow release. So you're making a better quality product that's easier to handle, easier to transport, easier to apply, that basically is more tailored towards the plant. So you get better yield and better performance in the plant, but at the same time isn't an environmental risk, that you're not getting leaching and you're also reducing the greenhouse gas emissions. So we started off at the lab scale where we do some lab trials like this in these little jars. And this is to really work out how these organic materials work on soils, how easily they're mineralised by the microbes. Do they help the microbes, the communities grow? So for instance, we might put the soils under stress, might put them under heat stress or drought to see if the microbes perform better when they've been given one of these products. We then move to the pot trial, so we can then scale up and just see how each of these products performs when we actually have a plant. Does it provide the plant with nutrition at the right time? And particularly under constraints. So we have a lot of drought here and heat stress. So some of our trials were basically putting the plants under stress. We saw benefit, the plants performed better when they had received one of these organic amendments. At the same time, we're looking at greenhouse gas emissions. In the pot trials, we're also seeing the leaching potential. And I'm pleased to report that as we go down the line, we get to this high-end product, we have less leaching potential. So this one, the raw product, is very quickly mineralised. There is a risk that the farmer's going to lose that, and it's also going to go into the environment and potentially cause eutrophication and damage the waterways. So by getting to these products, we're stabilising that nitrogen so it's released more gradually and when the plant actually needs it. These products definitely performed, so that was a really great result. So we did these trials both in the lab and we had a 2-year field trial where we ran these products out in the field. But what we're finding is when we're composting, particularly these products, and the further you go down with the compost, the more stable that compost is, it's actually encouraging the growth of methanotrophs. And methanotrophs are a special group of microbes that basically what they do is they take methane and they take it out of the atmosphere and they use it as their carbon source. So they're actually removing it. So it's a sink of methane, and so it can lead to reduction in greenhouse gas emissions. So we're not producing much, we're not a big strong emitter here, and we're also sucking it out of the atmosphere. So this is a great finding from this research. But what we want to do, we want to know what is the mechanism, why we're getting this. So we go back to this again to try and work out some of the reasons why these products are performing and encouraging the growth of these methanotrophs. But there are 2 types of methanotrophs. There's one that are dependent on copper and there's one that's dependent on iron. And typically it is the copper dependent methanotrophs that dominate in soils, but not WA soils. It is iron dominated soils. So we have a different group of methanotrophs than you normally particularly find in an agriculture soil. To identify them, we essentially do a DNA extraction, and the microbes that have taken up the heavy methane, their DNA will be heavier. So we do a DNA extraction. We then spin it really super fast over 2 days, and essentially what happens in that is the heavy DNA falls to the bottom. So the DNA from the microbes that basically remove the methane from the environment, they're at the bottom, and we displace the liquid in there, and we can then take out the heavy fractions, and we just basically sequence it. We just sequence it and find out who those microbes are, and from that we can then go back, find out whether it's copper or iron dependent, some more things about it, whether it likes carbon, whether it likes pH, some of these products will lime the system, and that liming has also been shown to encourage the growth of these methanotrophs. We can then remodify these products to make them even better. So overall, this product has multiple benefits when compared to a synthetic fertilizer. It's easy to transport, it's easy to apply, it's easy to handle, it can go down with equipment such as the air seeder, it output, no odour. It produces a crop yield equivalent with a synthetic fertiliser, but you actually even get benefits in protein gain. When we apply it, it has less leaching potential relative to synthetic fertiliser, so you're basically keeping the nutrients in the soil. And finally, it basically removes methane from the environment, so it actually has a less greenhouse gas potential compared to synthetic fertiliser. And this is really unusual about this product. It removes methane from the atmosphere.